Okay, here we go. So we're gonna go over the little quiz that we had the other day, and I found what I was hoping to be easier questions. You know, so understand that these would be on the easy end of questions, not just the norm. Okay, yeah. Hope that you get ones like this, but I'll hit you with some harder questions later too. Like the other day, I was struggling to do some of them. Yeah, there's some hard ones on the free response, but these were pretty straightforward. All right. So on part A, it wanted you to, if the radius of a cylinder is 1/3 the height, write an expression for the volume of water of the height at any instance. So the volume of a cylinder is pi r squared h. You'd get 1 point just for writing that down. Okay? And then you need to change your radius into 1/3 the height. Okay? And then, so that would be showing more work, probably another point once you got there. And then, if you square it out, it's 1/9 pi, and then h squared there and h to make h cubed, 1 point for that. So there's your 3 points, those 3 lines. Okay? At what rate is the height changing when the height is 10 inches? So we're talking about change. Anytime we talk about something changing, it's a derivative. So you take the derivative of both sides. So we only have one variable on the right side now, which made it nice. It wasn't 2 variables, just one. So dv dt, the change of the volume over a certain time, equals 3 times 1/9 times pi times h squared dh dt. A lot of you forgot dh dt. Okay? So that's the first step in this, taking the derivative. What? The derivative of h with respect to t. Okay? So it says the water is filling at a rate of 25 pi inches cubed per second. So that's the rate the volume is changing. So that's your dv dt. So 25 pi replaces that dv dt, equals 1/3 pi. And then when the height is 10 inches, so 10 is squared there, and you want to know at what rate the height is changing. Well, that's dh dt. Okay, that's what we're looking for. That's what we're solving for. Okay, so 1 point you earn just for knowing you're supposed to use a derivative on this. So showing a derivative here. So some of you got a point even though your derivative wasn't correct because you didn't put the dh dt down. You still got a point because you said, oh, I'm taking a derivative, and I could see some work for taking a derivative. Then some of you just went off the rails from there because you threw a 10 over here, and yeah. So, but another point is for knowing where to substitute numbers in and the working through the problem correctly. So pi's cancel on each side. So 25 equals 100 over 3 dh dt, because 10 squared is 100. So if you multiply by 3 100ths, dh dt equals 75 over 100, which is 0.75. And this would be inches per second, right? Yep, inches per second. So, Mr. Martin, when you skip from here to here, yeah, you can probably get full credit if you show this and this, but it's nice to show intermediate work along the way, okay? That's what you got to think in your mind as you're going through these, okay? Yeah, you got the full points, but I'm saying with him, he had very little written on his paper. So throwing down, Because sometimes the paper grader will throw you a point for some of your work, but if you don't have any, it's tough to throw a point at you. Okay? C. I guess I can be full screen here. Okay, C. What's the height of the water increasing what is the height of the water when it is increasing at a rate of 12 inches per second? Okay? So they want to know height. So we still stay with this same formula. dv dt equals, and then it would be basically 1/3 pi h squared dh dt. And then dv dt, we're still at 25 pi. This is still 1/3. This is still pi. We want to figure out what h squared is, and this is 12. So 1/3 of 12 is 4. Pi's cancel on each side. So 25 equals 4h squared. Divide by 4, divide by 4. And then take the square root, which is 5/2. 5/2 at what height? So 5/2 inches equals h. Okay? Because we divided by 4 and then took the square root. So 2.5 is also just fine to put down for an answer there. Okay? Number 2. Number 2 is also a derivative problem. F of x equals 9 minus x squared to the 3/2 power. And it says for part A, find the first derivative. Okay, which is 3/2 times 9 minus x squared to the 1/2 power. Remember the chain rule. That's part A. Okay? Times knowing that it's a negative 2x here. 1 point for that. Actually, 2 points for that. That's basically worth 2 points. And then you have to simplify. Negative 3x times 9 minus x squared to the 1/2 power. And there's your third point. Okay? B. B. Write an equation for the tangent line at x equals negative 2. Okay? So you find the first derivative at negative 2, which is negative 3 times negative 2 times 9 minus negative 2 squared to the 1/2 power. Okay, so then it's 6 times 9 minus 4 to the 1/2 power, or 6 square root of 5. Now, some of you rounded to the nearest 3 decimal places, to the nearest thousandth. That's fine. Okay, I think it was 13 point what? 13.416. Okay. All right. So that's the slope. Okay. That's a slope. Then you need to find the point. So then you had to find f of negative 2, which f of negative 2 is 9 minus negative 2 squared to the 3/2 power, which is 5 to the 3/2 power, which is 125, and the square root of that is 5 square root of 5, right? Square root of 5, yeah, 5 square root of 5. Or, well, I guess, so your point is negative 2, 5 square root of 5, using exact answers. So then you're going to put it in point slope form. Y minus y1 equals your slope times x minus x1. Okay, and then just solve. Did I do something wrong? Or am I right? Right? That's right. Okay. You did? What do you have written down?
I did f of 2, f prime of 2 instead of negative 2.
Wow. Merry Christmas, Dylan Reno. Okay, C. Let the function be that. Is it continuous there? So, we know that f of negative 2 equals 5 square root of 5. And then 2 times negative 2 plus 9 equals negative 4 plus 9, which equals 5. Since these are not the same number, no, it is not continuous. They have to be the same number, okay? I'm surprised they didn't ask about differentiability there, but they didn't. And the last one you just stick into your graphing calculator, because you could use a calculator on this. And what was it? Point what? Okay, 145.8. And I suppose you could have written it all out and all that, but for that one, you really don't need to write it out. If you're allowed to use a calculator and you can go straight to the calculator, you know, I don't know why they would require any work to be written out. Okay? We good with that? So that's that. Next thing. On Tuesday, we're going to have a quiz. A quiz over knowing stuff that you should already know, but even I forget it sometimes, as you've been witness to. But Tuesday's quiz will cover this. Your quiz will be second half on Tuesday. Tuesday, April 3rd. Not May 3rd. What? Okay, so looking at this paper, and I think I have it on my computer somewhere. Oh yeah, you don't sit where normal people sit. Yes, you are. Okay. Boom, boom. AP Calc. AP Calc memorization sheet. That's the one. Okay, so on this, the derivatives, the product. This is not how we really wrote the product rule as we were going through, but this is the product rule. So understand, when you're taking the derivative of two things multiplied times each other, it's the first times the first derivative of the second plus the second times the first derivative of the first. So the quiz, what you'll see is like this, and you'll be expected to know what it produces. You'll be given this, and you'll be expected to know what it produces. And as we go. What? given d dx of t over b, you need to know that that it's the denominator times the first derivative of the numerator plus the numerator times the first derivative of the denominator over the denominator squared on your quiz on Tuesday. Okay? So, as we go through there, you'll need to know that the first derivative of log base a of x is 1 over x ln of a, and so on. What? Oh, yeah, you can't, can you? You can, okay. I'm not writing on here. I wonder if I have a highlighter. Boom. Oh, I have a highlighter that works. Okay, sorry. So you'll be given this part, and then you'll have to provide this part. You'll have to know that part type of thing. Okay? No, formulas. Okay? Formulas. So you'll be given that, and you'll be expected to write that, and so on. So know the trig ones. Oh, now that my hand is the highlighter. So know the trig ones, and so on. So I'm going to talk about some of these. Speed and the absolute value of speed is the absolute value of the velocity. Not so worried about that one, but displacement and distance you'll be quizzed on, because you'd have to know which one uses absolute values and which one doesn't. Okay. Speed is increasing when velocity and acceleration have the same sign. That's not that big of a deal. All right, as we go. Then you'll have your integrals. Don't worry about this one. And actually, I will not put these 4 on the quiz. But understand the derivatives and integrals are just opposites of each other. Okay? But I'm not putting those 4 on the quiz. What? Oh. This one I'm not going to put on there either. What? You'll have choices down there for you. Yeah, so you won't have to write everything from memory. Okay, so there'll be a little bit given to you. Yep. Yep. So, disc and washer. Okay, know these. Okay, they'll appear on here, and cross section. I don't think I put that one on there. What I call the fundamental theorem of calculus is actually the second fundamental theorem of calculus. Okay, where we plug in and take the derivative. When you're taking the derivative of an integral and it's to this. Okay, so this one's a really important one. The fundamental theorem of calculus just says if you're taking the integral of a derivative, then it's basically f of b minus f of a. Then the average value of a function, I write mine differently than this. It's 1 over b minus a, I'll have it written, the integral of a to b of f of x. Okay. But besides that, yeah. So knowing this stuff, this is basically, if you know pretty much most all of this stuff, you know the basics of how to apply things on this test. Okay, so what are we going to talk about now? Well, we're going to talk a little bit about, I still have to go get that sheet. We're going to talk a little bit about things that we will see. And then after lunch, I'm just going to give you another practice sheet with like 30 problems, I think. I can't remember if it's the 15 or the 30, but have you just work through some problems again. But there's some things that we haven't touched on for a long time that we should probably touch on a little bit, kind of going through the chapters. Okay? So to be continuous, a point must exist at all points. So anytime there's an f of a equals b, there has to be a point for every function. And that the limit as x approaches a must exist from the right, and okay, to be continuous, these limits both have to exist and they have to be the same for it to be continuous. If you have a limit where you have this one different than this one, then it's not a continuous function. Because you could have something like this and like this, where every point is covered, every point has a point, but this limit going this way and this limit going this way are different numbers, so thus it's not continuous. Okay? So, or you could have something like this, and like this. Okay? This is not a continuous function because, not all the limits are the same. There's a number that exists for every point, but the limits have to be the same. Basically, they have to end at the same point. Okay? So we had that in chapter 1. We worked with limits where, remember, the limit of x as it approaches a of f of x plus the limit of x approaches a of g of x is really the same as the limit of f of x plus g of x as x approaches a. That you can add, subtract, multiply, and divide limits, and it's just like normal numbers. Okay? Some things that we might have forgotten that is if you have a limit as x approaches a certain number, let's just call it c, and it equals infinity, okay, what is occurring at c? C would be a what? A vertical asymptote. Okay? So if you're going towards a number and you have infinity or negative infinity, you're hitting an asymptote. An asymptote is happening at that place. Now, that's a vertical asymptote. Then, if x is going towards infinity and it equals a number, a limit of a certain number, then what is L? This would be a horizontal asymptote. So what's going on here is x is approaching a specific number, and so if c is right here and something goes towards infinity, that's going to be an asymptote. Where here, we're going out towards infinity, and it's staying at the same number. So if it was like this, and if we're going towards infinity that way, it's staying on the same y value, because this is a y value, then that y value would be a horizontal asymptote. Okay? So that's a little bit of memory jog from chapter 1 of limits and making sure we understand that. Now, a hole in a graph. Okay? What's different from a hole in a graph versus an asymptote? Where does a hole happen versus where does an asymptote happen? Well, a hole happens when we have something like this. When we have like x minus 2 over x squared minus 5x plus 6. Okay? This is going to produce a hole someplace. Why? Because the bottom factors into x minus 2, x minus 3, right? So at x minus 2's, these cancel. So that's where there will be a hole at the x minus 2. And here is going to be an asymptote. Okay? There will be an asymptote. So a hole happens where things cancel out. Okay? So you have to remember that because you're going to maybe hit a question and it's going to say something like, where is the removable discontinuity for this function? What is a removable discontinuity? It's going to be where a hole occurs. So where is the hole? Well, if you factor it, you can easily find that the hole is at x equals 2. Okay? And then at x equals 3, it's an asymptote. Okay? So little reminders of stuff from chapter 1 that was way back in September, basically. All right. So after that, we had chapter 2, which was just your very basic derivatives, all your derivative rules. Okay? So you might get hit with the limit definition of a derivative. What's the limit definition of a derivative? Well, that's a limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? And they might have a problem formatted in this format. And then you'll have to determine what's going on there. Okay? You'll have to determine like, oh, well, if it's f of x minus 2 minus f of x all over, and no, it wouldn't be like that. But understand this is a derivative. Okay, this is simply a derivative, and you might have to pull out some information out of there. Okay, now that's different than the numerical derivative, which is just f of x minus f of a over x minus a, which is just the slope formula. Okay, y2 minus y1 over x2 minus x1. That's why derivatives and slope are synonymous with each other. Okay, and derivatives give us the slope. All right. We all know the power rule. Okay. Power rule, product rule, quotient rule, and then all the derivative formulas, all the basic derivative formulas were from chapter 2. Okay. So that's where you need to know your sheet from. Okay. Chapter 3, we did the chain rule. Okay, so the chain rule is simply power goes out front. It's a power rule. Plus, or times, I should say, but in addition to the power rule, you have to take the first derivative of the inside. Okay, and that is the chain rule. What? Oh, they make it much harder than that, but I'm just going over some of these basic concepts of when did we learn this and that. Just a little reminders of that. Okay. All right. Yeah. Well, we're going to do another packet today, so we're just going to, you know, continue on with that. Okay. Unit 4. We were introduced to L'Hopital's rule. Have a good day today, Zaria. And L'Hopital's rule says this. If we have a limit as x approaches a certain number, where f of x over g of x gives you a 0 over 0, then we take the first derivative of the numerator and the first derivative of the denominator and find that limit, and that hopefully leads to something that is not 0 over 0. Now, sometimes you'll have to do L'Hopital's rule more than once, okay? If you still end up with 0 over 0, guess what? Then you're taking the second derivative of the top and the second derivative of the bottom. And then hopefully it is a non-zero number. Okay? So you might have to do that more than once. Okay? Okay. In this chapter, we learned that the first derivative of position is velocity. The first derivative of velocity is acceleration. Okay? Then we had related rates. So make sure you have memorized the cylinder formula, the cone formula, the sphere formula, and the cube formula. Okay? Know those volume formulas. So the volume of a cylinder is pi r squared h. They won't be up on the wall for you, okay, when it comes time for the test. The cone is 1/3 of that. Sphere is 4/3 pi r cubed. And a cube is just the side cubed. Okay. Knowing those are the types of shapes they use for their related rates problems. No, that's for just AP test. Yep, the AP test. Know those formulas because those are some of the more important ones. All right. There's one other one that I need. Ooh, I didn't put that one on there. Okay, there's something super important you need to know. And it's the difference between the tangent curve and the normal curve. And the normal curve is just a perpendicular. Okay. So, this was a little earlier this year, but tangent to a curve, the slope equals the first derivative, and the point is f of a equal b. If you're trying to find a normal line to a curve, it's the slope is the negative reciprocal of the first derivative. So it's a perpendicular to the slope. Okay? It's a perpendicular to the slope, still at the same point. So if you see a normal line, you gotta think perpendicular. Okay? Perpendicular to a tangent. It's going to be perpendicular to a tangent. All right? All right. So then we went on to the first derivative gives us a min or a max. The second derivative gives us what? Concavity. Okay, concavity. So if the second derivative is positive, it's concave up. If second derivative is negative, it's concave down. And then you got to mix and match a little bit where, okay, let's say this is the first derivative curve, okay? And this is like negative 1, 1, 2, 3. Where is this concave down? Where is it concave up? Well, if this was the original curve, it would be all concave down, right? But this is the first derivative, so what is happening there? Where is it concave down? It's concave down from negative infinity to negative 1, because it's where the first derivative is negative, is where it's concave down. Because if you take the second derivative, it's blah, 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 blah. Okay? So, and what's this point called? Nope. That would be a maximum point there, because it's where the first derivative is equal to 0. So this would be, on the original graph, this would be a downward slope. Wait, so this is increasing. Actually, this is concave up, because it's increasing the whole time. Come on, Mr. Bierschbach. You got to think through this. So, whoops, right there. So this is actually all concave up here because it's always increasing. So this is concave up. This is a negative slope up until negative 1, and then a positive slope for the original graph. Okay? But yeah, since it's always increasing. All right. So every once in a while I say stuff I'm not supposed to. Okay. Mean value theorem. There exists a point where the slope at point C equals the average slope from A to B. The slope at C, somewhere in between A and B, should be equal to the average slope of that. Okay, mean value theorem. Extreme value theorem is in between 2 points. There's always going to be a min and there's always going to be a max. And then the rest of it we got to was integration, and then we got to differential equations. So after lunch, you're going to have work time to work on a packet. The packet's not graded. We're going to go through the packet tomorrow. Okay? If you want to ask me about questions on the packet today during class, you can. So that's what we're doing today after lunch. Okay? So there you go.